Good morning, chemical engineers, and welcome to Chemi Feud. I am your first host, Lehri, and today we will be testing your knowledge of flows in packed beds. The rules of the game are simple. When a question is finished being asked, buzz in and answer the statement in the form of a question. We have a wide array of questions, so let's meet our contestants. Our first contestant is Flynn Baliton. Our second contestant is Bianca Elsea. Question 1. This type of drag results in a tangential shear stress on a smooth surface parallel to the direction of flow and is exerted by a fluid on a solid body in the direction of flow.
What is skin or wall drag?
That is correct!
As you can see in this diagram here, the streamlines represent the path of the fluid element. They flow at a constant velocity until they reach the surface of the object, where they result in a tangential shear stress parallel to the surface of the object in the direction of flow. The skin or wall drag is exerted on the fluid by the solid in the direction of flow.
Question 2. This type of drag incurs additional frictional losses when a fluid is not flowing parallel to a surface and must change directions to pass around a body.
What is an eddy?
I'm sorry, that is incorrect.
What is form drag?
Correct!
As you can see in this diagram, the fluid changes direction to flow around the solid object. The point as it hits the front center of the object is called the stagnation point, and the fluid velocity is 0 and the boundary layer growth begins, as you can see by this purple dashed line. Further along, it starts to separate, resulting in a wake covering the rear of the objects, which is made up of large eddies, which are these little things right here. The frictional losses due to the fluid changing directions is called form drag.
Question 3. For flow past an immersed object, this value is defined as the total drag force per unit area to rho v0 squared over 2.
What is the drag coefficient?
Correct!
As you can see, this first equation is the equation for the drag coefficient, where FD is the total drag force and the area AP is the projection of the area perpendicular to the direction of flow. Rearranging this first equation, you get the equation for the total drag force and the Reynolds number, which is given by this equation, where G0 is rho V0. Depending on the shape of the immersed body, the relation between CD, FD, and RE will be different. Increases in the Reynolds number result in the separation of the boundary layer and shifts in separations causing wakes to form. When the Reynolds number increases to a specific point, the boundary layer becomes completely turbulent and results in a significant drop in the drag coefficient.
And it's time for bonus feud. This question will be worth double the points. In this question, air flows past a sphere. Given this set of values, find the drag coefficient and the force on the sphere. That is correct.
So for the solutions, first you need to calculate the Reynolds number value. This can be used with this equation, plugging in all of the values, and you get 5.781 times 10 to the 4th. Using this and the figure that was given to the contestants, you can see that the CD value following the line for spheres will be equivalent to 0.47. Then you can use the drag force equation and plug in all of the values again, and you will get 0.1958 newtons for the force.
Now for round 2. Question number 5. The ratio of volume of voids in a bed to the total volume of a bed is...
What is void fraction?
That is correct. The void fraction is represented by the symbol epsilon. This number is an important part of analyzing flow in packed beds. Packed beds are important in chemical processes for use in catalysis, adsorption, absorption, and so many more applications. The theoretical approach to solving relations for packed beds is regarding packed beds as a bundle of uniform tubes. Therefore, the void fraction comes into play when defining the fraction of void space where fluid can flow. Question 6. The ratio of surface area of a particle to the volume of a particle is?
What is specific surface?
That is correct. The specific surface of a particle is given by AV is equal to SP over VP, where SP is the surface area of the particle and VP is the volume of the particle. The units are meters squared. For example, the specific surface for a spherical particle becomes 4 pi times dp over 2 squared over 4/3 pi times dp over 2 cubed. This gives us 6 over dp. Question 7. The units for the following equation are?
What are meters?
That is incorrect.
What are 1 over meters?
That is correct. A represents the ratio of the total surface area in the bed to the total volume of the bed. If surface area has units meters squared and volume has units meters cubed, this results in A being equal to 1 over meters. Question 8. This number is represented by the following equation.
What is the Reynolds number for a packed bed?
That is correct. V prime is a superficial velocity defined as epsilon times v, where v is the average interstitial velocity in the bed in meters per second squared. The hydraulic radius RH is defined as epsilon over A. Thus, for a spherical particle, RH equals epsilon over 6 times 1 minus epsilon times dp. For example, the equivalent diameter d for a channel is d equals 4RH. Thus, plugging into the Reynolds number, you get the following equation. Ergen defined the general Reynolds number as the above without the 4/6 term, or what was stated in the original statement. Question 9. The Blake-Kozeny equation shown here is valid under these conditions.
What is laminar flow, a void fraction less than 0.5, effective particle diameter, and a Reynolds number less than 10?
That is correct. Combining the Hagen-Poiseuille equation with RH and the superficial velocity v prime, that gives you the following equation. Experimental data shows that the constant should be 150 under these conditions, which results in the Blake-Kozeny equation as shown in the original statement. Question 10. In highly turbulent flow through packed beds, this variable approaches a constant value.
What is friction factor?
That is correct. The first equation here is derived using the same process as in the previous question, but using the equation for change in pressure of turbulent flow. Since the friction factor approaches a constant value, this gives rise to the Burke-Plummer equation for turbulent flow through packed beds. The constant value, 1.75, is representative of the friction factor, which is experimentally determined. If we add this equation for turbulent flow to the equation for laminar flow, we get a general equation for low, intermediate, and high Reynolds numbers. Using dimensionless numbers, it becomes this equation, where G prime is equal to V prime times rho.
Jumping right into round 3, we're starting off with a bonus feud question. This question is about a pressure drop and flow of gas in a packed bed. You have air flowing through the bed and you're given these values here. Calculate the pressure drop.
The final answer is...
That is correct. Approaching this question, the first thing you need to do is solve for the cross-sectional area. The cross-sectional area is given by pi over 4 d squared. You know d, so plugging in d, you can solve for a. Then you use your value for a to solve for g prime, which is given by the mass flow rate divided by area. Once you have your g prime, you also need to convert your pressure into pascals. After doing that, you want to use the Reynolds equation to solve for the Reynolds number, because you have all of those values. Plugging in you get 13.21. After that, you need to solve for the average pressure, which is given by P1 plus P2 all divided by 2. Because you don't know P2, you have to use a trial and error method. So the first guess we could guess is that P2 is equal to 1.065 times 10 to the 5th pascals. If you choose that P2, then you can solve for your average P. And using your average P, you can plug it into this equation right here to solve for your average density. Once you have your average density, you can plug it into the, this is your average density, sorry. After you have your average density, you can plug it into the general equation for flow using the dimensionless form. Solving for that, you can solve for your delta P, and you can see that your delta P is approximately equal to your original guess, therefore it's good. On to question 12. This is the ratio of the surface area of a sphere having the same volume as the particle of interest to the actual surface area of the particle.
What is the sphericity shape factor?
That is correct. The sphericity shape factor is used to help simplify calculations for irregular shaped particles. The shape factor can be found using this equation, pi dp squared over sp. Sp is the actual surface area of the particle, and dp is the diameter of the sphere having the same volume as the particle. Once that is calculated, you can use it to solve for AV, the specific surface, and A, the total surface area over the total volume. Question 13. The equations below are used for this type of particle flow.
What is mixed particle flow?
That is correct. The answer was mixed particle flow. This equation takes into account the shape factors of varying materials where the dpm is the effective mean diameter of the mixture. On to question 14. For laminar flow in packed beds, the flow rate is proportional to blank and is inversely proportional to blank and blank.
What is proportional to delta P and inversely proportional to viscosity and length?
That is correct. Using the Blake-Kozeny equation shown as the first equation, we can find V prime. And V prime is equal to the flow rate over area, which is then equal to negative K delta P over mu delta L. From this relationship, we can see that the flow rate is inversely proportional to mu and delta L and directly proportional to delta P. Now for question 15. The equation below has a Reynolds number range of what values in a pressure dropping minimum fluid velocity system? Here's your equation.
What is 0.001 to 4,000?
That is correct. The minimum fluid velocity is given by this equation here in terms of the Reynolds number. If the Reynolds number is less than 20 for small particles, the first term can be negated from the equation. If the Reynolds number is greater than 1,000, then the second term can be negated from the equation. If you have Vs values and Ms values are unknown, then this equation has been experimentally determined to be reduced down to the first equation shown in the initial problem statement. That equation can only be applicable for Reynolds number values of 0.001 to 4,000. These values have a standard deviation of plus or minus 25%. And now for our second to last question, question 16. The relationship between the velocity and the pressure drop in an upward flow through fluidized beds causes this when the fluid reaches a speed in which the particle just began to move.
What is maximum fluidization?
I'm sorry, but that is incorrect.
What is minimum fluidization?
That is correct.
At low velocities, the particles remain stationary. They do not move until the minimum fluidization velocity is reached. Once it is reached, the pressure will drop, or the pressure drop will increase to a value that is equal to the gravitational force on the particles when multiplied by the cross-sectional area. The porosity at this stage is described as the minimum porosity. Once it reaches a higher velocity at a certain speed, the pressure drop will decrease and the particles will remain unchanged as the fluid bed expands and the porosity increases with increased velocity.
And now on to our final question, and this one is a bonus feud. And this question is going to be on the expansion of fluidized beds. Using the values below, estimate the maximum allowable velocity, VF, using an operating velocity of 3 times the minimum, estimate the voidage of the bed.
The answer?
I'm sorry, but that's incorrect.
My answer?
That is correct! Woo!
Okay, as you can see here, using the approximate equation to calculate the operating range, you plug in the VMF value to get the final velocity, which is your maximum allowable velocity. Using an operating velocity of 3 times the minimum, you are able to get your final operating velocity here. And to determine the voidage at this new velocity, you substitute into this equation here, using the known values for minimum fluidization conditions to determine K1. And once you have your value for K1, as seen here, you can use this equation to solve for your final porosity.
Let's give a big round of applause for our winner, Flynn Baliton! Thank you so much, Flynn.
Thank you, Sana.
We hope you had a great time and took some great notes too. To summarize, we talked about the different drag and friction forces, flow past spheres and cylinders, flows in packed beds, and flows in fluidized beds. See you next time on Chemi Feud. This is Sana Lehri reporting from Chemical Engineering at the University of Florida. Okay.
Oh, Question number 5. The ratio of volume of voids in bed to the total volume of bed.
What are meters?
Yeah.
The sphericity shape factor is used for irregular shaped particles to simplify the flow calculations. Moving on to question 14. For a laminar flow in a packed bed, moving on to question 14. For laminar flow in a
Hello, welcome back. Oh wait.